Right. Well, happy Monday. It's week 5. We're almost halfway through this quarter. Some of you are just a few weeks away from graduation. So yeah, we'll keep going here. Okay. So we took a small detour and we looked at neural networks and I posted homework 3. I posted it this weekend, but I imagine a lot of you were working on Data Fest and stuff like that. So I wasn't fully anticipating people really getting into it. But homework 3 is about neural networks and it's been posted. And so take a look. It's going to be due next week. You do have to derive the gradients for the loss function with respect to the bias matrices. And so then, that's a bit of work. But once you work through that, hopefully, kind of the code that I've provided and some of the examples I've done in class will help guide you through the process. And I hope it's interesting. So anyway, so we did neural networks. And so now we will go back to kind of where we left off in the textbook. I guess we're only at chapter 2 now. But we'll look at kind of the maximum likelihood approach for kind of learning things. And so we're going to take a look at least squares regression again. All right. And I know it's like, oh, I've seen this so much, and I see it in 100C, and I've seen it in 101A, and all of these things. But it does form a good kind of starting point, just because we are very familiar with it, and so we can kind of bring up a lot of these things. And so anyway, we're going to take a look at linear regression, but from a maximum likelihood estimation perspective. And do you guys already do this is it 100C or 100B where you do it from an MLE thing? Okay, well, anyway, so we'll take a look at it and we'll throw it into kind of some optimization functions anyway. And we'll also take a look at kind of Fisher information, but that's in a future lecture here. Okay. All right. So again, with linear regression, you've got your kind of your weight vector, your vector of weights, which is basically your coefficients. You multiply that against your x values. This is for the nth observation. You're going to take your vector of coefficients, your w vector, you multiply it by xn, and that's going to form your predicted value, right? And a lot of times in your in your xn, you have a constant like 1. So that's going to form the intercept when multiplied by your weight vector. And when we did, when we took the approach of the mean squared error, we said, we want to find the values of the weight vector of our coefficients that are going to minimize the difference, minimize the sum of the residuals, right? So the residual is the actual value for observation n minus the predicted value for observation n squared summed up. 1 over n is the mean squared error. And that's going to be our predicted value, the coefficients that we use, the fitted values to be had. Okay, or in vector notation, it's, we're finding the w's that minimize the, this expression here. Okay, so that's what we did. That was right before we did the neural network stuff. And, we said, we're going to take the loss function. We're going to, define some kind of loss function, and we're going to estimate the model parameters by minimizing the loss function. And we did it via, we did it via calculus. We also did it via gradient descent. And today, rather than looking at the loss function, we're going to look at the likelihood function. Okay, and now rather than trying to minimize the loss, which is the difference between the actual and the predicted values squared, we're going to look at the likelihood. Okay, and so this requires us to create a probabilistic model where we're going to have likelihoods of data points, right? So the probabilistic model says, basically there's a mean value, and then and that's kind of like the signal, but then you have noise, and therefore the values that get generated are, you know, centered around the mean value, but there's error, right? And so in our generative model, we're going to say that this is kind of the signal part. This is the mean value around which things should be should generate, but all of the observed values that we see are subject to random noise. Okay, and so this is going to form, you know, some kind of prediction line, and that's the mean value. And then we're going to say, you know, this is the relationship that exists in the population, but again, any individual value, there's going to be some error term, some epsilon, okay, and that's going to, you know, represent kind of the noise, and therefore the observations we observe might be larger or smaller than whatever the mean value is. Okay, and so this looks a lot similar, okay, than kind of what we had when we were trying to minimize the loss function. We said, you know, t hat is basically going to equal this mean function, you know, the vector of coefficients multiplied by, you know, our x vector, right? And so the only difference is that we're saying the actual value is basically equal to, you know, what our model predicts, the model plus error, right? And this is kind of a common structure that you see in a lot of any kind of linear model, or you know, a lot of other models, is you have, you know, basically what the model is predicting, okay? And it might not be, you know, in a linear model, this is a linear model, right? This is a linear combination of w times x, but you can have any other kind of model, right? So the model part is just this part, this t hat, whatever this t hat is, that's the model. And then you always have an error. So this could be, you know, some logarithmic expression. This could be, you know, logistic thing. You can have whatever thing you have, but basically the data is always going to be kind of whatever we have, and anything we can't capture here is we just throw it into error, okay? And basically different models differ by how it's able to predict t hat, okay? And so I think this is very familiar to us. Actual value is our prediction plus error. Okay, and so now that we have this error part, the error is random. It's now a probabilistic model, okay? And so, you know, versus the, you know, way back here with the loss function, this is kind of more so, it's not not deterministic, but we just have this thing where we say, you know, the x's that are coming in we treat them as fixed values. The t's that we're predicting are also fixed values, and we're just trying to find some set of w's that minimize this. Okay. Now over here, the values t are not treated as fixed values, but are values subject to random noise. Okay. So this is a probabilistic model, and therefore, you know, the observations we have, you know, they come from some kind of distribution, and we're going to try to calculate the likelihood of the data itself. And what we want to do is we want to select the model parameters that will end up maximizing the likelihood of our data. Okay, so whatever data we have, we're going to say, well, what are the values that are going to maximize this? Okay, so here is our linear model. Okay, it's, you know, the linear part plus the error. All right, and the key assumption here is that we are going to assume that this error term is random. Okay, it's centered at 0, and it follows a normal or Gaussian distribution. Okay, we're going to assume that the errors come from a Gaussian distribution. All right, if we don't assume that the errors come from a Gaussian distribution, then what we're going to do in the next slides will not work. Okay, and that there's constant variance, sigma squared, right? So so that's actually a key assumption that that we're making, and that's why, you know, I think in 101A there's a constant emphasis that, you know, you want to check your model assumptions and model conditions, and one of the big assumptions is that you have constant variance, and if you don't, you call that heteroscedasticity and whatever, and then it doesn't work. Okay, or you have to say, well, caution. All right, so here we're going to say, the error terms are normally distributed, centered at 0, sigma squared. And therefore, if I combine this along with this, okay, basically, we're going to say the actual values that we have observed, t sub n, come from a normal distribution where the mean is given by this thing. I'm just taking this and then plugging it in and basically adding this, right? And then now that I've got some error, it's gonna look like this. Okay, and so this is just my junky drawing here. If you got this random noise here, the idea here is that this, I don't know what happened with my picture, but this blue line represents what you get when you fit the linear model. The linear model represents kind of this straight line, and the values that we've observed, these dots here, are basically just, if you were to take a small slice here at this location, at this particular x location, we're expecting values to be normally distributed, and so values close to the line are expected, right? It's centered at this line, and values far away are less likely to happen. Okay, and basically where this normal distribution is centered is going to shift as your x sub n position changes here. Okay, and obviously it doesn't have to be a straight line. This W transpose xn can take on any kind of shape, as long as it's a linear combination of your x variables. In this case, I guess I just have kind of one x variable, and the predicted values is going to be a straight line. But if you have, it's going to still work. Some linear combination of whatever your x variables are. Your x variables could be, polynomial in nature. All we're doing is we're just adding some random noise around it. Okay. All right. Is that good? Does that make sense to everybody? All right. Let me give you your first view quiz answer for today. View quiz answer today is B. B as in bear. B as in bear is your first view quiz answer. Okay. So now that we have a probabilistic expression for every observation in our data, we want to find the model parameters so that we can maximize just the total likelihood of observing the data we have, right? What's the difference between a likelihood and a probability? Or a likelihood function, we'll say a likelihood function and a probability distribution function. Maybe that's a little bit more specific. Difference between a likelihood function and a probability distribution function. Is there a difference? So a probability distribution function will integrate to 1, okay? The probability density can actually, the density is not restricted to be 0 and 1. The density itself can be, can go higher than 1. The cumulative distribution function will go from 0 to 1. And when you integrate the probability density function, it's going to integrate to 1, or if you have the probability mass function, it's going to sum to 1. Whereas a likelihood function, it does not have to integrate to 1, okay? Because the likelihood function is a function of the parameters. And if you integrate the likelihood function across all possible parameter values, it will not necessarily integrate to 1. All right. So here's just a quick review of maximum likelihood estimation. I know you guys already covered this in 100B, but in the past, some students have kind of forgotten how MLE works. So this is just a very, very, very quick review. Please don't be insulted that we're going over this here. Okay. So, let's say I've got some kind of pouch. All right. And I've got 10 marbles in this pouch. I'm going to say 3 of the marbles are red. The rest are blue. And so therefore, when we draw a marble, okay, the marbles itself have a Bernoulli distribution, and the probability of drawing a red marble is going to be 3/10, okay? And so when we talk about this, we're going to say the probability that x equals 1, given that theta, this is the hidden parameter, the unknown parameter. Well, right now, it is known to us the parameter is going to be 0.3, and therefore, the probability that x equals 1 using kind of the PMF of the Bernoulli distribution, which is theta to the x, 1 minus theta to the 1 minus x. We plug in 0.3, this becomes 0, this becomes a 1, right? 0.7 to the 0 becomes 1, and then so this evaluates to 0.3. This is great if we know what theta is. But in general, we don't actually know what theta is equal to. And so, we have to kind of figure this out here, okay? When you take a sequence of independent events, right? So we're gonna draw marbles with replacement, right? So I'm gonna draw a marble out and I put it back. I'm gonna ask, what is the probability of getting this exact arrangement, this exact sequence where the marbles go red and then we put it back and then we mix up the bag and we get another red, I'm eating some trail mix here, but if I pull out an M&M, here I got a red M&M, and I shake it up and I say, all right, well, now I got a cashew, but what's the probability I'm going to get this exact sequence? Okay, well, if we know that the probability is 0.3 for red and 0.7 for not being red, okay, which is everything else is blue, then we know this sequence of getting red, red, blue has to be 0.3 times 0.3 times 0.7, and the total probability is going to be 0.063, okay? This is asking for the exact sequence of red, red, blue, which does not, which is different from binomial. So the binomial probability mass function includes an n choose x, in this case 3 choose 1, and that would be 3 times bigger than this. But here we ask for this exact sequence versus what's the probability of getting 2 red and 1 blue in any order. Okay, so when we talk about probability functions and likelihood functions, they both describe probabilities, but the distinction is this, okay? Right, a probability function is a function of the outcome x, right? So here we're asking what's the probability of getting these outcomes 1, 1, 0, okay? Or this outcome x equals 1. So that's the probability function, and we're going to we leave the parameter theta as fixed, and we can change the outcome x, right? And therefore, the probability functions have to sum to 1 over all possible values of x, and it has to integrate to 1 if values of x are continuous. So if we look at this function, when x equals 1, we get 0.3, and when x equals 0, we get 0.7, and those two values would add up to 1. Here, if I treat theta as fixed to be 0.3, and I talk about every single combination of 1s and 0s I can get for x, we would have 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, there's 8 possible combinations, and all 8 of them would sum to 1 if we take all of those probabilities, okay? Whereas a likelihood function, on the other hand, we're going to treat the data as fixed, okay? We're going to treat the data that we've observed as fixed, and we can modify the value of the parameters. And we can say, for this exact outcome of data, what is the likelihood of getting this particular outcome of data if theta were, instead of being 0.3, what if the pouch was a mystery, and what if we set theta equal to 0.5 or theta equal to 0.7 or theta equal to 0.1, right? And so we're going to leave the observed data as being fixed, and we can change the parameter theta, right? So we both have x and theta in our functions, but the probability function theta is fixed, and we're changing x. Over here with the likelihood function, x is fixed, and we're changing theta, okay? And so when you change all of the theta values, the likelihood function is not going to necessarily sum to 1, and it's not necessarily going to integrate to 1 either. All right, question says, then can we think of likelihood sort of as the opposite of a probability function? I mean, opposite is a little bit of a weird word, right? Like what's the opposite of a cat? I don't know. A non-cat? A dog? I don't know. What's the, not cat, right? So what's the, it's a little bit strange to think of the opposite of a likelihood of a probability function, right? We got some good answers, right? So dog's the opposite of a cat, or a mouse is the opposite of a cat. And it's all like, or the not cat, right? An antimatter cat. Is there such a thing? I don't know. So I hesitate to use the word opposites, but they're related concepts. And I know in just daily language, we use these words interchangeably. What's the probability? What's the likelihood? What's the chance? These are all kind of just like synonyms. But, at least, for a statistician, they have distinct meanings. And so the probability, when you integrate them, they'll integrate to one. You're changing the outcome X, you're leaving the theta fixed. Likelihood, you're changing the value theta, you're leaving the X's fixed. Likelihood related to odds ratios. You can do odds ratios, but you can also do odds ratios with probabilities too. So odds ratios is kind of like a value that's derived from probabilities and likelihoods. So not necessarily necessarily one is restricted to the other. All right. So anyway, now I had a pouch somewhere. Well, I don't know what I did with it. Well, we'll just use my trail mix bag. And so this time we're going to say, all right, I've got this new, a new bag, and we don't know exactly if the marbles are red or blue, or what proportion is red or blue. But we're going to, when we draw some pieces of candy out, we get the sequence. We got a red on the first one. I shake it up, I put it back, I get a yellow, we're going to say not red. Okay, we get the sequence red, red, and blue. Okay, we're going to call red 1 and blue 0. And so we're going to say, what is the likelihood? What's the likelihood? Okay, and that is if this is a function of theta, all right, we're going to treat X as fixed. We're going to treat this sequence 1, 1, 0. This is a fixed thing. We're going to say, okay, well, what is the likelihood of getting our data for some particular value theta, right? And so we're going to take the probability function, and we're going to just kind of take the product of these three probabilities for the different X's. And basically, well, in the first one, my X is 1. And the second one, my X is 1. And in my third one, my X is 0. Okay. And so when I take the product of these things, the exponents get added together, and we're going to get theta squared times 1 minus theta. And that's going to be the likelihood of this function, of this data, 1, 1, 0, if I change the different values of theta. Okay. So we're going to say, because we got basically two reds, and the probability of red is theta, and then we got one blue, which is going to be 1 minus theta, right? And so now, did I plot this? I never plotted it. All right, so if I were to plot this, let's go to Wolfram Alpha, and then I'm going to just do a to the squared times 1 minus a to the 1. Okay, so this is what the plot looks like. Can I zoom in on this? Enlarge, please. Oh, I have to pay for that. All right. Look at that. I can just zoom on the browser. Okay. So anyway, this is what the likelihood function looks like from 0 to 1. Okay. And we can see, the likelihood is highest around, 0.67, something around there. Okay. And then if I integrate this, I'm going to go from a equals 0 to 1. Okay, so this thing does not evaluate. This does not evaluate to 1, right? If I integrate this from 0 to 1, this evaluates 2.08333, right? And that seems like a slightly odd number, but it's just it doesn't evaluate to 1 because certainly there are other possible outcomes other than getting this sequence 110. We can get 101 and things like that. Okay. All right. So when we do the maximum likelihood estimation, basically, we want to just find the value of theta that's going to maximize this likelihood. We're going to say, Eric, when we plot this, when we plot this thing, what value? So this is the likelihood function. What value of theta? So the theta can go anywhere from 0 to 1. What value of theta is going to maximize this, right? So when you have the visual plot, you can say, oh, you know what? It's going to be right around here, wherever this is, 0.67, 0.66. That's going to be the value that maximizes it, right? And we can see, if theta were equal to 1, it would be impossible to get our data, right? Because if every single marble in our bag is red, then it's impossible to have gotten the blue one. If theta were very low, if the probability of getting a red marble is very low, the probability of getting this exact outcome is also very low because we happen to get 2 red of them, right? So if only 1% of the pouch is red, it's very unlikely that you draw 2 red marbles out of the thing. All right. So anyway, when you try to deal with the derivative of this thing, it gets a headache, right? Like you have to deal with product rule and all sorts of stuff. So what we often do is we just say, you know what, let's turn everything into a log. Okay, we take the log of everything, and then and we're going to take the derivative of the log. That's a lot easier because everything gets turned into when you take a product, the logs turn everything into sums, and then you can take the derivative of that, and so you find the derivative of the log likelihood. The log likelihood is this, and you solve for where the derivative is equal to 0, right? You want to maximize the log likelihood. So rather than maximizing the likelihood itself, we're going to maximize the log likelihood. And because the log function is monotonic, wherever you maximize the log likelihood, it's going to be the same value that maximizes the likelihood itself, right? Okay, so anyway, you take the log and theta squared becomes 2 log theta, and the log of 1 minus theta is log of 1 minus theta, and then we take the derivative of this. Derivative of the log becomes 2 over theta, and then the log of this is 1 over 1 minus theta. With chain rule, it becomes -1. You multiply by -1. So then I move it over to the other side and multiply both sides by the denominator. So I get theta over here times 2 times 1 minus theta. You get 3 theta is equal to 2, and therefore the theta that maximizes the log likelihood is going to be 2/3. Right? So this is all okay, right? So we want to find the value that does that. Okay. So anyway, so that's basically the value that maximizes this, and that coordinates exactly with argmax. Yes. Oh, no. Okay, so if you ask Wolfram alpha, indeed it says A is 2/3, and it's right here. This is our plot. Okay. All right, so if we go back to linear regression, we would just want to find the value of W that's going to maximize the data that we've seen, this T here, okay? Oh, you know what, before I do that, let me give you your second view quiz answer. Today is D as in dog. D as in dog is your second view quiz answer. D as in dog. Okay, so there was a question, why not just take the derivative of theta squared minus theta cubed? Where is that? Oh yeah, we could have easily done that, all right? Easily. I could have just multiplied this out and done theta squared minus theta cubed, and we would have gotten the same exact answer, okay? This is just to get you in the habit of taking logs and then deriving that and solving, okay? But yes, this absolutely would have been easy. I could have just multiplied this out and I've got theta squared and theta cubed, and I could have solved for theta and gotten the exact same answer. Because over here, it would be a headache dealing with this product, okay? And so the trick is we're going to take the log and deal with that. Okay, so we're going to assume all of our observations are independent of each other, and therefore when you assume all of these things are independent of each other, the total probability of all of your observations is going to be the product of individual probabilities, okay? And therefore, the total likelihood of our data is going to be the product of each of these things, right? So we've got the normal distribution centered at this mean value, W times W transpose X sub n, and then we've got constant variance sigma squared. Okay, and so here is the PDF of the normal distribution, okay? And so we're gonna do this, okay? So we're gonna plug this in and solve. So I'm gonna take, I plug in the PDF of the normal distribution here, and we're gonna say the likelihood, okay? And so these are all gonna be treated as fixed values. Our data, the observed observations T, the observed input values X, these are fixed. The sigma squared is also assumed to be fixed. And the only thing that we are modifying, okay, the theta that we are modifying, or the parameter that we're modifying, is the vector W, okay, the vector of coefficients W. And so the mean, okay, so back here we're doing X minus mu. Okay, this mu is defined by W transpose X sub n. So we're going to put that right here, okay? And then our X here is our T sub n. Whoops. Okay, so this is what we have here. We're going to have the product of a bunch of sigma over square root of, so it's square root of 2 pi sigma squared, but you can extract out the sigma, e raised to all of this. Okay, so when you take the product of this, it's going to be a huge mess, but we're going to take the log likelihood, okay? And so again, just to kind of reiterate, this function is a function of W, right? So that when we're talking about the likelihood function, we're going to say, what's the likelihood if my slope were this and my intercept were this? What's the likelihood of my data if my slope was a different number and what is the likelihood of my data if my slope was 2 and my intercept was 3? What's the likelihood of my data if my slope was 1 and my intercept was 0.5? And we would get different values. We'd say, if the mean line looked like this, your data is really unlikely. If your mean line looked like this, then your data is a lot more likely to happen, okay? And so we're not trying to minimize errors. We're trying to say, you know what, looking at where our data is, this line seems a lot more likely, this line seems a lot less likely, okay? And we're assuming everything else is kind of fixed values. We're assuming our observed values T are fixed, our observed values X are fixed, sigma squared is a constant. The only thing that we're trying to mess around with is basically the slope and intercept, or whatever values are in our coefficient vector. And we want to find the coefficient vector that, that maximize this. Yeah, I got typos all over. Yeah, okay. All right, so here's the likelihood. We're going to take the log likelihood, right? So you take the log of this, that's going to turn the product into a sum, right? It turns multiplication into addition. So we're going to get the sum of this, and we're going to get basically the log of every expression here. So the 1 over square root 2 pi becomes, we're going to get the log of 2 pi raised to the negative 1/2, right? So that's going to be log of 2 pi raised to the negative 1/2. So we get 1/2 log 2 pi. 1 over sigma is basically sigma to the negative 1. So we're going to get negative log sigma. Over here, I've got e raised to all of this. E raised to all of this, just the log of that gets rid of the e. And so we just get all of this part. Okay, this part just becomes here because the log cancels out the exp, which is convenient, right? And then, so now I have the sum from n equal 1 to big N of all of these terms. These are all constants. And so when you take the sum of n of them, you're just going to get, it's just going to be multiplied by a big N here, okay? This is also a constant with respect to W, right? So the only thing that's being modified is the W, okay? And so with all of the different W's that we have, this is just going to become big N here, all right? And then the summation just applies only to this part over here, okay? And so I have negative 1, 2 sigma squared, and now we are trying to maximize this term, Tn minus W transpose Xn squared, okay? So now we're trying to maximize this, and this is multiplied by a negative 1, okay? So we're going to take the derivative, we're going to set it equal to 0, and we're going to solve, right? So we want to find the value of w that's going to maximize this. Okay, so this, if I take the derivative of this with respect to our vector w, okay, this is a constant. So with respect to w, it's going to become 0. This is also a constant. So that becomes 0. All right. The square term here is going to cancel out when I take the derivative of it. The 2 is going to cancel out with this 2. So I'm left with -1 over sigma squared. And this, so I get t minus w transpose xn. And then I apply the chain rule to this term here. So with respect to w, I'm going to multiply this by negative x over n. Okay, and so just to kind of make sure that our derivative kind of makes sense as far as dimensionality goes. All right, so this is a constant. This is just a scalar value. Xn is a 2 by 1 vector. Okay, and then this is a scalar. Tn is a scalar. W transpose xn is a scalar. So here I just have a 2 by 1 multiplied by a scalar thing. Okay, and I can kind of apply this and expand out here. All right, so I've got xn here, and then this part I can also multiply here, and I've got xn. When I distribute it over here, I've got a 2 by 1, and then I'm going to multiply it over here. Okay, so I've got, so here I'm just kind of distributing my xn thing, and so that and that makes sense because if our w, if we're assuming this to be a 2 by 1, the gradient with respect to w is also going to be 2 by 1. All right, so here we have this, and if we just kind of say, all right, well, how does this all work out? Okay, so here I've got the sum of x transpose xn t. So this is a 2 by 1, and I'm going to kind of distribute the summation term. So we've got the sum of xn over tn minus the sum of xn transpose w. Okay, and so just to remember, this is what our xn looks like. It's our 2 by 1, and big X can be thought of as each individual x kind of transpose. So this is going to be a column of 1s and a column of the x values. And so if I want to go, if I want to try to get rid of the subscripts here, okay, so looking first at this term, if I get rid of the subscripts here, I've got a summation of 2 by 1s, which means the sum of everything has to remain 2 by 1, okay? And so if I go from each individual xn, and I kind of turn this into big X for all n terms, we're going to have big X transpose, which is going to be 2 by n, and t, which is a n by 1 vector. This will remain a 2 by 1. The result X transpose t will remain 2 by 1 here. Is that okay? Going from the summation of xn tn can be done by calling this X transpose t. Right. Similarly, I have xn transpose w, right? And again, xn individually, xn is 2 by 1, xn transpose is 1 by 2, right? So this multiplies 2 by 1 by the 1 by 2 becomes a 2 by 2, and I multiply that by w, which is 2 by 1. So this results in a 2 by 1. So the summation of everything is 2 by 1, which we need. And again, I can take, when I want to drop the n and use big matrix X, this is going to be X, big X transpose, which is going to be 2 by n. I'm going to multiply that by X, which is n by 2, and I can multiply that by W. So I'm going to get X transpose XW. So this part, so I'm going to have 1 over sigma squared. This part is equivalent to X transpose T, and this part is going to be equivalent to X transpose XW, this part with the summation. Okay. So we're going to say the gradient of the log likelihood with respect to W is equal to this. Okay, so now that we have that, we're going to take the gradient of the log likelihood with respect to W. We're going to set that equal to 0 and solve for W. Okay, so when you do this, all right, the sigma squared term cancels out. You can add x transpose x w to this side, and then you're going to multiply both sides by the inverse of x transpose x, right? So if I just kind of, like, I skipped a step here, but I've got x transpose t is equal to x transpose x w, and I multiply both sides by x transpose x inverse. And so I get x transpose x inverse x transpose t is equal to w hat, right? And this is a very familiar quantity to us. This is the exact same solution that we had earlier that minimized the sum of squared error, minimized the mean squared error, right? And then, we derived this way back in week 1. This is the exact same solution, right? And that just kind of tells us that minimizing the squared loss, so minimizing sum of squared error, mean squared error, is equivalent to maximizing the likelihood if we assume the errors come from a Gaussian distribution, okay? An interesting thing is that, the sigma squared doesn't appear in our solution at all. It's a constant, and it doesn't affect the W that we choose, right? So whether you have a high amount of variance or high amount of noise or a low amount of noise, as long as it's kind of Gaussian and constant, it's going to just drop out, okay? And the solution for the W hat that we should pick just that doesn't care what sigma squared is, right? This so I kind of just want to point out, like, it's not a coincidence that it works out this way, okay? So if we look back, right? So if we look back to the Gaussian, the reason why it's equivalent is if you look at the expression for the normal distribution. So the normal distribution looks like this, okay? That part x minus mu squared, okay, when we write down our likelihood function, okay, we have Tn minus W transpose Xn, right? And when you take the log likelihood of all of this, here you get, as far as W goes, here we've got constants, here we've got constants, okay? And then the log likelihood, we got the log of the exponent, okay? So that just drops out, and now we have basically the summation of this, and this is multiplied by a negative here, right? And this part over here, this is the sum of squared errors, right? We've got Tn minus W transpose Xn. This is equivalent. This is the sum of squared error, right? And we're taking each observed value T, subtracting off what our model predicts, W transpose Xn, okay? And so when you take the sum, that's just the sum of squared error. It's multiplied by a negative, right? So it's not multiplied by -1, 2 over sigma squared. This is going to be a negative value, okay? And therefore, when we're trying to maximize the log likelihood, that's exactly equivalent. This is going to be maximized because it's multiplied by a negative here. It's going to be maximized at the same spot where this quantity is minimized. So when we minimize the sum of squared error, it's exactly equal to maximizing the likelihood and the log likelihood because this is the sum of squared error here. All right. And again, this thing only appears if you assume your noise is normally distributed, right? So if you don't assume your noise is normally distributed, okay, if this part, this comes from the normal distribution, if this part were not true, then this quantity would not appear, right? This sum of squared error term does not appear in our expression. Okay, and so anyway, that's that. That's just a derivation of showing that the maximum likelihood estimation term for for linear regression ends up being the same as minimizing the sum of squared error. There's a little bit more that we can do with this, kind of getting into Fisher information, all of that, and so we'll continue this discussion on Wednesday. But for now, this is just kind of a brief review of MLE stuff, and we've applied it to linear regression here. Okay, we'll end here for today. Let me give you your last view quiz answer. Last view quiz answer is C as in cat. C as in cat is your last view quiz answer for today. Okay, have a good evening. Good luck with your homework, and we will see you guys on Wednesday.